Hi, everybody. Welcome. I'm Anna Harvey. I'm the president of the Social Science Research Council, and welcome to our College and University Fund lecture series. So this year, which you know if you've been coming to these lectures, we're focused on the question of how do we do, or do we want to do, research that actually solves problems? And we're hosting researchers who are asking questions like, what is it that we're trying to accomplish with our research projects? So how much should we be prioritizing internal validity of our findings? How much should we be prioritizing external validity or generalizing our findings? How much should we care about whether our research findings are actually implemented in the world by somebody? And depending on what our answers to those questions are, what would we need to do differently, if anything, as we design our research projects? And what additional kinds of infrastructure and support might we need to achieve the particular mix of goals that we might be trying to accomplish in our research projects? And one thing that I think we've seen emerging this year across disciplines is increased interest in addressing not only internal validity, which we've been focused on, I think, in many of our disciplines for quite some time now, but also can we preserve the internal validity of our research findings while also caring about external validity or generalizing and implementation. So we're seeing people start to focus on those two latter questions. And today we are very happy to welcome one of, I think, of the pioneers who's been encouraging us to think harder about not just internal validity, but also in particular external validity and generalizability. Duncan Watts. Duncan is now the Stevens University professor and 23rd Penn Integrates Knowledge University professor at the University of Pennsylvania. Duncan is a computational social scientist. He holds faculty appointments in the Annenberg School of Communications, the Department of Computer and Information Science in the School of Engineering and Applied Science, the Department of Operations, Information, and Decisions in the Wharton School, and the Department of Sociology in the School of Arts and Sciences. And he also directs the Computational Social Science Lab at Penn. So Duncan has a wide breadth of disciplinary expertise and interests. And today, Duncan is going to tell us whether we're doing social science backwards. Duncan is going to talk for about 40 minutes, and then we'll have time for Q&A. So you can put questions into the Q&A box on your Zoom screen at any time. And after Duncan is done, I'll get brought back out and I'll field questions to Duncan for the rest of the time. So feel free to use the Q&A. So Duncan, thank you for being with us today, and the floor is all yours.
Thanks, Anna. Thanks for inviting me. It's really fun to be here and to get to talk to you all about this work. Let me just share my screen. We can get started. Let's see. Here it is. Okay. All right. So this is joint work with quite a few people who are listed here, and I'll show their names again. As we go. Just try to hide my hide myself here so I'm not blocking my own screen. All right. Okay. So I want to start by giving an example, a concrete example of what I'm talking about, just to try to make it clear. The example that I'll return to later on is related to this question of group performance and what causes it. And so, sorry, my computer's a bit twitchy here. Can I go back? Here we go. So this is a problem that has come up in many fields, in psychology, in management, sociology, economics, and more recently in complex systems and computational social science. And the question is, roughly, of all the things that go into a group, the people, the leadership processes, the structure, the task, the environment. What are the things that cause some groups to do well and others to do poorly? So this is certainly a very interesting and important academic question. It's also a very interesting and important applied question. And given that, a large fraction of the economy in one way or another relies on teams and groups to perform tasks, it's something that a lot of organizations care about and spend a lot of time thinking about in practice. And so with all of this attention over all of this time and all of this sort of real economic value at stake, what have we learned? And the answer is that we have learned lots of things, many results, decades of results that refer to all sorts of predictors of performance, like ability level. And so some of these predictors have to do with the people in the group, others have to do with how the people interact, others have to do with the context. And so there's many results out there. But there's a problem with these results, which is that they have a tendency not to agree with one another. So let me just pick one particular example from this list, the communication networks. And so if you read the literature on networks and team performance, you can find papers that have the result or claim the result that as the network becomes more efficient, in the sense that the average shortest path length goes down and the speed of communication goes up, the performance of the group goes up with it. But you can also find equally well-published and cited papers that claim the exact opposite result, that as the networks become efficient, then the performance goes down. And there's interesting theoretical reasons why one might expect that to be true also. And so there's nothing particularly special about this result. And in fact, you can find similar contradictions in the literature for essentially anything that you care to look at, whether it's the efficiency of the networks or the skill level of the people or the diversity of the people in the team. There are papers out there and studies out there that will support each conclusion, its opposite conclusion, and also the null finding. So the result of all of these results is that we know many little things, but we don't know how those things fit together. So they are what I call incoherent. So where does this coherency come from? Now, one possible explanation is that some of these results are just wrong. And as we all know, we've been going through a replication crisis for the last decade or so, and we have a much clearer understanding now of why some results in the published scientific literature simply aren't true, potentially because of small sample sizes, but also this sort of larger problem of researcher degrees of freedom and publication bias. And as a result, we have a surprising and worrying number of false positive findings out there in the literature that fail to replicate when we look at them more closely. And so some of this incoherence could result simply from some of these findings being wrong. But what I want to claim today is that even if we solve that problem completely and all findings were 100% replicable, this incoherency problem would remain. And what I want to argue today is that there is in fact a deeper problem going on here, which is what I'm going to call the one at a time paradigm for social and behavioral science. So what is this one at a time paradigm? Well, it's nothing special. In fact, it is exactly the paradigm that we have essentially all been using for our professional lives, which is we start off with some hypothesis. So we have a theory about why people do what they do, or in this case, why groups do what they do, and we articulate that theory, or we develop that theory into a hypothesis, such that if true, then some intervention that we can imagine in some context that we can imagine should have some outcome that we can predict that's consistent with the hypothesis or confirms the hypothesis and therefore is consistent with our theory, right? So this is a sort of common universal way of thinking about science in general, and including social and behavioral science. And so having come up with that idea in our heads, we proceed to design an experiment. And so let's imagine this experiment sitting in a two-dimensional space. In reality, it's, as I'll explain, it's much higher dimensional, but let's say one of these axes is describes the intervention that we are going to design, and the other one is the context in which we're going to implement it. And so our experiment occupies one point in that space. We then run the experiment, we get some result. Hopefully it's the result that we were expecting, or if it's not, it's something that's sort of surprising in an interesting way, and we get to write up our findings. And when we do that, we implicitly or explicitly generalize the result using the theory that we are articulating to apply more broadly than the exact point that we studied. And in some cases, we make very sweeping claims, and we make some sort of assertion of universality, or at least we make that claim explicitly. And in other cases, we're more careful, and we acknowledge that, of course, you know, our theory can't explain every possible, or the result that we got wouldn't apply to every possible intervention in every possible context. There's some sort of boundaries in this space, but very rarely, if ever, do we explicitly articulate or formalize what we expect those boundaries to be. And so we're kind of vaguely waving our hands and arguing from our theory that the result that we found applies more generally, right? We almost never, and I think probably never, write the paper in such a way that we only make the theoretical claim for the exact manipulation that we chose in the exact context that we chose. If that were what we were to do, then nobody would find it interesting. Okay, so here's the problem, that we generate that result, and then other researchers over you know, potentially many years do a similar thing, essentially follow the same process many times, and all of us are asking generally the same question. In this case, we're all asking about what causes team performance, but because we're different researchers, and because we come from different disciplines, and we are operating in different time periods and possibly different countries, or at least different institutions, we make all kinds of different choices about the exact intervention that we're going to design and the exact context in which we're going to implement it. And so implicitly, and the implicit part is important here, implicitly we are all sampling different points in this space and very likely coming up with different results. Okay, so the colors here indicate that we're finding different results. And so time goes by, lots of these papers pile up, and then somebody comes along and says, okay, what have we learned? And the problem is it's unclear what we've learned, right? That in fact, we have a version of Rudyard Kipling's famous poem about the blind men and the elephants, where we're all exploring a different part of the problem and reaching some incompatible conclusion about what the thing is that we're looking at. Okay, so let's dig a little deeper here. Why does this happen? I mean, what I described to you as the one of the time paradigm doesn't sound anything different from the scientific method that we all learned in high school, and you know, I think actually it is the same thing as the scientific method, and we are led to believe, I think, with good reason, that that method has worked pretty well for science in general. So what's going wrong here? And the argument is that theories in the social and behavioral sciences are different than theories in fields like physics in a particular way, namely that they are imprecise, right? So whereas theories in physics are typically written down as mathematical formula that make very precise predictions, often numerical predictions that can be falsified in such a way that if the predictions are wrong, then the theory is wrong. That's almost never true in the social and behavioral sciences. In fact, our theories tend to be verbal, they tend to be vague, they're often consistent, equally consistent with opposite outcomes. They rarely make specific predictions, especially numerical predictions about the magnitudes of expected outcomes. They rarely, if ever, specify under what conditions they should be expected to apply. And they rarely, and I think probably never, specify how they're supposed to interact with all the other theories that are out there supposedly about the same thing. And so as a result, when two experiments reach different conclusions, it's really impossible to say what, right? I mean, I think that's a fair claim. And again, in theory, we have processes that are supposed to help, particularly research synthesis procedures like meta-analysis or systematic reviews are supposed to help in theory, but in practice, they run into the same problem. Like, how are you able to summarize the results of many studies when the studies themselves differ in ways that you're unable to articulate, right? So clearly, they're different, but if you can't say how they're different, then it's not clear how you're supposed to aggregate them. Okay, and the other sort of related point is that when every point in this space is being generated on a timescale of a few years, then the aggregation of knowledge is extremely slow, and lots of things can change in between. So it becomes almost impossible to run experiments in an apples-to-apples way, just for this practical reason that the last experiment that was run probably got run a few years ago. Okay, it turns out that we're not the first people to make this observation, and in fact, there's a really wonderful paper that I recommend reading called "Playing 20 Questions with Nature," that was written by Alan Newell, one of the founders of artificial intelligence, back in the 1970s. And he characterizes the traditional or the pervasive way of doing psychology at the time as in terms of this quiz game, 20 questions. And so he says the proper tactic is to frame a general question, hopefully binary, that can be attacked experimentally. Having settled that bit's worth, one can proceed to the next. The policy appears optimal. One never risks much. There is feedback from nature at every step, and progress is inevitable. Unfortunately, the questions never seem to be really answered. The strategy does not seem to work, right? And he then goes on to say that the problem is not that the results themselves are wrong. The problem is that we can't put them together because innumerable aspects of the situations are permitted to be suppressed. So there's no way of knowing whether anything is commensurate with anything else. He then goes on to make a prediction that even though the papers that he's talking about were excellent individually, he couldn't convince himself that it would add up even in 30 years or more of trying, even if one had another 300 papers of similar excellent ilk. So we're now 50 years beyond that, and there's not 300 papers, there's hundreds of thousands of papers, but I think the prediction holds. Okay, so why has nothing changed, right? If Alan Newell pointed this out 50 years ago, why are we still doing things exactly the same way that we were doing them back then? And there's lots of possible answers to this question, potentially one of which is that other people didn't agree with him and don't see that there's a problem. But the one that I'm going to focus on today is that there hasn't really been any alternative, right? That this is the way that we learn how to do science. It seems not only the obvious and natural way, but it's sort of unclear what you would do if you weren't doing this. If you weren't doing what I'm calling the one at the time paradigm, what would you do? And so what I want to outline today is such an alternative. And I'm going to call it integrative experiment design. And so this framework really flips the one at a time paradigm on its head, hence the title of the talk about doing things backwards, except in some sense, we're doing things forward right now. Maybe we should do them backwards. And the basic idea is that instead of starting with a theory and then designing an experiment to test the theory, instead start at the end of the process, at the generalization end of the process, and ask yourself, what is the space of experiments to which I want my theory to generalize? So what are of all the things that I could vary in my experiment? Let's imagine each of those things as a parameter, and the variation of that parameter is a dimension in this space. And now I can construct some high dimensional space, and I can do it explicitly. And that's the important part here, right? Rather than just implicitly picking some point in the space, I'm going to explicitly define the space, say what these dimensions are, say how I'm going to measure things along each of these dimensions. And now every point in this space is some potential experiment that I could run. Now, if you think about this for a moment and think about all the decisions that you have to make in designing an experiment, you'll see that this space can get very large very quickly in terms of its dimensionality, and it becomes overwhelming. So in practice, we have to choose some subspace which is motivated either by an application of interest or some sort of theoretical consideration about generalization. So you have to make some choices, and I'll give an example in a little bit. But the key idea is to start with this space and to be explicit about where everything is located in the space. Now, having done that, you start sampling points, right? So you pick a point, that point corresponds to an experiment, you run that experiment. Pick another point, you run the experiment. Now, I don't want to get into the details of sampling because there's lots of different ways to do it. You could just do it randomly. You could do it according to some adaptive experimentation algorithm. You could use a bunch of experts to suggest different points to sample. You could have a meeting and talk about it. You could come up with it yourself. There's lots of ways that you could use. But the important point is to start sampling these points, run the experiments, and then fit some kind of model to the results. So again, there's lots of ways to do this. It could be a linear regression. It could be some fancy machine learning model or a deep neural net. Any of the above is potentially fine. So lots of ways to do the modeling. But the important part is to do the modeling and use that model to make predictions about points in the space that you haven't sampled yet. So even if it's just a simple linear model, as soon as you fit that model, it immediately is making predictions about every other point in your space. You then want to sample some of those points and evaluate your model. You then keep doing that, looping around these two steps of sampling points, running the experiments, and making new predictions until you're satisfied. And once again, there's no sort of universal rule about how to be satisfied. Potentially you run out of money, potentially your model converges, potentially you get to some accuracy of prediction that you're happy with. There's different rules you could use, but at some point you stop. And only then at the last step, do you interpret the model in terms of theory, right? So again, this is flipping everything on its head. Rather than having the theory first, you have the theory at the end. And so you interpret the regions in your space that you discover where different results show up as consistent with different combinations of existing theory and possibly even new theory. So this, for those of you familiar with Robert Merton's classic paper on theories of the middle range, sounds a lot like theories of the middle range, but is much more explicit and formulaic about how those ranges are defined. Now, at that point, you may decide to repeat the whole process, right? And we can get into that later. You may be unsatisfied with the space that you have considered. You might now have new ideas about that you want to test, or new ways that you want to generalize the theory, and so you may go back to step one again and repeat the whole process as necessary. So this is the general idea, and we published this idea in a paper recently called Beyond Playing 20 Questions with Nature. This is with Abdullah Al-Matouk, Tom Griffiths, Jordan Suchow, Mark Whiting, and James Evans. Okay, so we argue that this procedure, this framework, has some natural advantages. It automatically integrates results from many experiments into a single consistent model. So you get around, you immediately solve this incoherency problem. Because it makes predictions and incorporates the information from all of the experiments. It's always falsifiable. It's always adaptive. You don't have to sort of worry about p-hacking here because the proof in the pudding is always some prediction that you're making out of samples. So you're always keeping yourself honest, no matter how much data mining and overfitting you do at each stage of this process. You've always got another stage where you're exposing your model to as yet unseen samples. And so you will discover how well your model performs in reality. You're also not stuck with the design space that you start with. And you might be asking yourself, how do you do that? How do you come up with a design space? Well, we'll talk about that. But the real answer is it's unclear. And there's lots of reasonable things you could do, and different people would come up with different solutions. And so part of the learning process is also learning what the design space should look like. So maybe you discover after running many of these experiments that some of your dimensions are essentially the same and you don't need all of them. And so you can get rid of them. Maybe you discover that there are points in your space such that if multiple experiments map to the same point, you're getting different results, which shouldn't happen. So you must be missing some dimensions, right? Or maybe you discover that there's some question you can't even ask because you don't have the relevant dimensions in your space. And so you need to add them. And all of that's fine. You can add dimensions, you can get rid of dimensions. And so the whole process is meant to be adaptive, right? You don't have to get everything right at the beginning in order to learn how to get the right thing at the end. That's part of the appeal of this framework. And the claim is that the result will be more replicable, cumulative, and useful. So you get these boundary conditions that delineate these theories of the middle range. And by focusing on predictive accuracy, you can quantify how useful your theory is or your model is for any application. Okay, now obviously there are many challenges to doing this. It's one thing to propose this in theory, it's another to do it in practice. I just mentioned defining the space is tricky, sampling from the space is tricky, running a large number of experiments, hundreds, thousands, potentially hundreds of thousands of experiments in a consistent way while varying potentially many parameters is extremely challenging to do from an engineering perspective, but also from a methodological perspective. Analyzing the data is tricky. Reconciling the results, interpreting the results with theory is tricky. So there's every part of this process is something that we're currently trying to figure out. And so I talked a lot about this in the abstract. I want to go back to the example that I mentioned at the beginning about group performance and show you how we tried to do this in a very specific case where we are predicting what we call synergy as a function of the task. So this is a work, again, with Abdullah Al-Matouk, but also Emily Hu, Mark Whining, Lamia Gandhi, and James Halton. And we're inspired in this by this very nice book by James Larson, which is called In Search of Synergy. And so here's the question, is it better to have more people working on a task or does adding people to a group cause more problems than it's worth? And one way to quantify this or to measure this is in terms of what Larson calls synergy, which is defined as when a team outperforms a similarly sized or as he calls it, nominal group of individuals who are working independently. So a nominal group has the same size as the team, but rather than working together, they work independently. And so that kind of keeps things apples to apples in terms of the number of the resources available. And so the hypothesis of this experiment is that whether you find synergy or not will depend on the task that is being performed. And there's a lot of indirect evidence or evidence for this general claim. Certainly people have looked at this problem over, again, many years, and it does indeed seem that that task type has potentially a large effect, but it's unclear what it is about the tasks that is causing synergy to appear or not appear. Okay. Whoops, I'm going backwards. Okay, so step one, again, we want to construct this space. So if we want to explore how synergy depends on different types of tasks, we first need to have a language for describing tasks. And there are, in fact, in the literature, many frameworks or taxonomies for describing tasks that have been proposed theoretically. It turns out they're not really commensurate with each other either. And so what we do is we go through several of these taxonomies and we extract their underlying features, and we create a space of about 24 dimensions that refer to different theoretically important or potentially important features of tasks. We then go to the literature on experiments, the experimental literature on team performance, and we find from reviewing hundreds of papers different tasks that people have studied in this literature. So contexts in which people have said, I want to understand team performance, I'm going to have my team do this particular task or these two tasks. We then extract those tasks and featureize all of them according to the features that we have extracted from the frameworks. And we have currently about 100 of these tasks. So effectively what this looks like is a big table where the rows are tasks and the columns are the dimensions or features that we have extracted from the literature, and each cell has a number, which is the extent to which that feature applies to that task. And these numbers currently all come from trained human raters who are looking at a very structured version of each of these tasks. So we have a whole process for producing these structured descriptions. We have a bunch of raters who then give their individual ratings, and we average these ratings, and that's the value of that coordinate in the space. So each of these tasks is then mapped to a point in the space. So as a result, we have these 24 features that correspond to different taxonomies in the literature. And the map looks something like this. So this is, of course, a two-dimensional projection of a 24-dimensional space. So don't interpret it too much, but it gives you some idea of the tasks that we're looking at and how they are scattered around this space. Okay, but we don't actually rely on these two dimensions for any of our analysis because we want to preserve the whole 24 dimensions. Okay, so we've got the task map, right? Or what we call the task map. The task space is the space. The map is the set of 102 tasks distributed in that space. So then we start sampling. So we start off by implementing 10 of these tasks. We then implement these tasks using the Empirica platform, which was developed by Abdullah and a bunch of other people. For each of these tasks, we create low, medium, and high complexity levels, because complexity, we think, also matters. So we have 3 versions of each task. And then each one of these 3 versions of each of 20 tasks is then completed either by an individual, a group of 3, or a group of 6. So we have 3 group sizes, 3 complexity levels, and 10 tasks, sorry. We then run the experiment and we measure individual and group performance, which allows us to compute the ratio of the 2. That's what, if the ratio is above 1, we call that synergy. And in this case, we also follow Larson by distinguishing between weak and strong synergy. In weak synergy, we compare the group to a randomly chosen member of the nominal group. And strong synergy is when the group outperforms the best performing member of a nominal group. So if we're looking at a group of 6, we'll sample 6 individual people, and then we'll pick the best of those 6, and that's what we'll compare the group to. We then fit two different models, a linear regression model and a neural network. We could have chosen others to this data. And that's the end of phase one, right? We can evaluate the in-sample performance of these models, and it looks pretty good. But that's not what we care about. What we care about is how well these models will perform on tasks that we haven't looked at yet. And so what we do now is we use the models to generate predictions for 5 new tasks that exist in our task map, but we haven't done experiments on yet. We make predictions for each of the models for weak and strong synergy for each of these 5 tasks, and then we write those down and pre-register that. We then go and implement these new tasks. And by the way, implementing each of these tasks is about a month worth of engineering time because you have to build a whole new user interface for every task that you do. And then we run the same experiment, the same experimental procedure on these new tasks and evaluate the predictions as we did before, refitting. And then finally, we refit the model on all 15 tasks. So we evaluate it we evaluate the models on the new tasks, but then we pull in all of that data because we want to learn, and we refit the model on the full data set, right? And then we repeat the process again with phase 3, where we do exactly the same thing that we did in phase 2. So we've now basically completed the whole loop, and now we have 20 tasks at the end of these 3 phases. We could, of course, keep going, and that is the goal is to keep going, but this is enough for now. So what are some results? This is sort of all the data in one figure. There's 20 rows here for the 20 tasks broken up into the three waves. You can see that we have almost 6,000 observations here, where an observation is a team of a particular size or an individual performing one of the tasks at one of 3 complexity levels. We have over 1,200 unique participants who are allocated between the individual condition, the n=3 condition and the n=6 condition. So just to put this in context, this is the scale of this experiment is about 40 times the size of a paper that we published just a couple of years ago, in which we were looking at this same question of synergy for a single task. So that paper was published in PNAS. I think it was a good paper. I think it's pretty typical of many papers that are published in this literature, and was actually probably on the larger side in terms of the number of conditions that we looked at and the number of participants. And this one's about 40 times that. So you're sort of it's almost like replicating an entire literature in one experiment. I'll also just note, because the typeface is small, that the columns on the left-hand column refers to team performance, the ratio of team performance to a random individual corresponding to what we've been calling weak synergy. And on the right, it corresponds to the team performance relative to the best individual, and the dashed vertical lines are at 1. So performance in excess of 1 is indicative of synergy. Okay, so I'm not going to get into this in great detail. Again, these results are pretty hot off the press. I was hoping that they would be in better shape by now, but we're still, of course, working on them. The main result I want you to pay attention to is there's a tremendous amount of heterogeneity, that we observe weak synergy in a bunch of tasks, strong synergy in some tasks, and no synergy in one task. And this is at a very high level consistent with prior work, which has essentially found all of the above. Sometimes sometimes teams display synergy, sometimes they don't, sometimes it's a mixture. But I want to emphasize that this is not all explained just by the type of task, because there's lots of variation even within one of these sort of classical task types that comes from the literature. You see a lot of variation even within a task type. And so what we want to do now is switch to prediction and say, okay, let's use all the features of all of these tasks and use these models to see how well we can predict tasks that we haven't trained our models on. And because we always like to use some sort of baseline, how does that compare with a different model where you only use the features of the individuals in the team, right? So you know things about the people, maybe that could tell you whether you expect them to have synergy or not. And so we want to compare our task-based models with group composition models. And so this is admittedly a hard slide to read, but I'll just tell you what the results are. The top figure is showing you the out of sample R squared for the linear model, which is in red, and the neural net, which is in blue. The wave number is indicated in the box. So there's two indicates wave 2, 3 indicates wave 3. The top half of the figure refers to strong synergy, the bottom to weak synergy. And in each case, the top line is the models that use the task-based features, and the bottom line is the one that shows the group composition. And really all you should get from this is that the task features are doing much better than the group features. The best performing model is about an R squared of about 0.37, which is pretty good compared to other prediction exercises that we've worked on. And that's for the neural network in wave 3. But whether you think that's good or not, it's a lot better than R squared less than 0, which is what you get for all of the group composition features, which is in effect worse than just predicting the overall average for everything. And then finally on the bottom, we can do some feature importance evaluation, and the x-axis is the feature importance evaluated for the strong synergy model, and the y-axis is the feature importance for the weak synergy model. And you can see that they fall pretty much along the diagonal, which is good because it means the same features are sort of roughly as important for strong and weak synergy, which is nice. And roughly speaking, the features that are most important are correspond to some notion of objective correctness. So if we were doing the final step of the procedure, which we haven't really done yet, we would want to sort of interpret these findings in terms of existing theory. And so if we were looking back at the literature on task taxonomies, then something around objective correctness seems to be an important predictor of an important feature in predicting performance. Okay, I'm almost out of time. So I'll just very briefly mention that we're going to keep working on this project, and then there are other follow-up projects also about team synergy. We want to look at, obviously, we'd like to study more tasks. We'd like to look at other types of outcomes beyond synergy, maybe group satisfaction or psychological safety. We're also interested in expanding the dimensionality of the space. But in addition to pushing forward on team synergy, we also are looking at other applications of this integrative design. I've talked in detail about one problem, but you can effectively do this for anything. So we're doing it for public goods games and looking at the efficiency of punishment in public goods games. We're doing it for nudging across different contexts. We're doing it for small group deliberation around matters, issues that are politically polarizing. And we're doing it for team communications and performance. And so in each one of these cases, we are adopting the same general approach of integrative design, but the specific way that we do all of the steps is different from domain to domain. And then finally, I know Anna mentioned at the very beginning a point about infrastructure. We're also trying to build the infrastructure to make it easier for other people to do these sorts of experiments. So that this is not just a one-off thing that can be done by one lab, but becomes something that can be done as easily as the existing one-at-a-time paradigm. So with that, I'll say thank you. These are the papers that I've referenced in this talk. And at the bottom is a plug for Empirica, which is the platform that we use to run these experiments. So I'll stop sharing now and take some questions. Thank you.
Great. Well, thank you so much, Duncan. I am going to take the privilege of asking a question before we get to the Q&A. And my question is about something you said on your last slide, next to last slide about, you can use this method for any kind of question. And my question about that is when we face constraints on our ability to sample in the design space. And so just a couple examples. One example might be one thing that you've held constant in these team experiments is that they're all conducted on your platform, right? And so we might wonder, another dimension of the design space could be, what if we were testing these in the field in actual organizations? But I think we're going to face constraints with actual economic and social organizations in terms of what they let us randomize, right? There are certain economic concerns and ethical concerns and that all kinds of things that arise.
Yeah.
So we're going to have, we're not going to be able to sample the full space. And in fact, something we've seen when people who are say fielding multiple RCTs is that the organizations that volunteer to be part of the RCT consortium or whatever are not going to be a random sample for particular for bias reasons. So that's one. So it's just like, and another one I was thinking of is, say we're, the scale is a constraint. So we're, it's a an intervention to increase the contribution of teachers to children's education, and in small scale we're working with we can hire the best the story that we can hire the best teachers, but as we scale up we can't, we've hired them all already. And so but I think your method is that we have to run the experiments at all points of we have to sample from all points of the design space, but there might be some that we're simply constrained. So I was wondering if you thought about those kinds of practical constraints.
Yep, we have. Those are great questions. And you're correct on that all of them are different from what we did. Let me break it down a little bit. There's the platform that we are using here. It's a very good platform. It has lots of nice advantages, but the method is not platform specific, right? So you could actually run the experiments anywhere, right? In order to integrate them, all you need is there's really just two rules here, right? The first rule is be explicit about the design space so that you can locate whatever it is that you're doing in the design space. And the other one is, force your model to make predictions, right? Like that's it. That's it, really. Those are the only two things. Everything else is sort of up for grabs, including like the platform that you run on, right? So yes, it's easier to run hundreds of experiments, recruiting crowd workers online. But if the goal is to study people in the field, then by all means study people in the field. And the data is still, as long as the data can be expressed in the same language, right, using the same dimensionality, then it's no problem, right? Now, that doesn't mean that everything is feasible, right? So there are, of course, as you know, lots of experiments that you can't run, either because they're too expensive, or organizations won't agree to do them, or they're unethical, or for whatever other reason. Our method doesn't have a solution to that problem, right? Like you're sort of stuck with that. You can only integrate the results of the experiments that you can run, right? But I still think it is better to integrate the results of any number of experiments than not to, right? So, even if you only do 2 experiments, it's still better to learn from both of them than to run 2 incommensurable experiments and now not know what to do with the results. So in a sense, I would say this method works for any number that's bigger than 1, right? Now, of course, running lots of them is probably better to have more data than less data, but a simple sort of back of the envelope calculation will show you that as the dimensionality of the space goes up, the number of possible experiments becomes astronomical very quickly. And so in no sense are you ever going to be able to exhaustively sample the space, right? So you're always going to be using a very sparse sample of the space of all possible things that you could have conceivably done. And then you're relying on the model to make predictions about everything else. And so a lot does depend on the model, but you're keeping yourself honest by forcing the model to make predictions. And the same thing, so that also applies to your second point about scale. If it's just very difficult or expensive to run an experiment, you're just not going to be able to run very many of them. But you're still better off, and we would argue you're still better off learning what you've learned from the experiments that you were able to run, right? Now, in the worst case scenario, it might turn out that even with all the experiments you've been able to do, you can't predict the next experiment, right? It's just, there's too much randomness, or there's too much contextual dependency, or there's too many dimensions and interactions, and you're just, you don't have enough data to be able to do a good job of predicting the next thing. So, and that actually does happen and has happened to us. And that's disappointing when it works out like that. But I think, again, I would say it's better to know that than not to know that, right? It's better to know that you don't have enough information to make a good prediction about the next thing that you plan to do, versus fooling yourself into thinking that you do because you ran some experiment and you're just imagining that it's going to generalize, right? So, at the very least, you can avoid fooling yourself into thinking that you know things that you don't know, right?
Yeah, no, totally. I agree with all that. Okay, so we have a million questions, which we're not going to be able to get to all of them, but we're going to get to as many as we can. And then we're going to keep typing your questions if you have them, because we're going to send them all to Duncan ex post if we're not able to get through them all. So we have two questions. One is about, can you say a little bit more about why you don't like meta-analyses, including standardized meta-analyses? And also, can you be a little bit more explicit about what's the difference between your use of the term "quote unquote" model as opposed to a theory of the range of different contexts in which an intervention should work?
Great questions. So let me just preface this by saying something that I don't want to forget to say, which is that if you go and look at the BBS paper that is referenced at the end, we received many commentaries about the paper, which are published with the paper itself, along with our response to the commentaries. So it's very likely that some of the questions that people in this audience have are the same questions that other people had when they read the paper. And so if you go and check that the BBS paper, you may see that we have already responded to your concern. So hopefully that will address some of the questions that people won't get a chance to ask. With respect to meta-analyses, I do like meta-analyses. I don't not like meta-analyses. I'm definitely on team meta-analysis, right? But meta-analysis, what my comment was that meta-analysis basically is stuck with the same problem, which is that it can only work with what it has, right? So if you have a bunch of studies that are all extremely similar to each other, that's helpful because you can sort of aggregate them without worrying too much about all of the incommensurability that might exist. But now you have you have difficulty generalizing, right? You're sort of stuck with the same problem that you don't know what to predict for different studies. And if you're trying to run a meta-analysis across very different types of studies, you don't, because authors, and we've discovered this the hard way, don't specify all of the details in a way that, in a consistent way, it becomes very difficult to say how the different studies that you're trying to aggregate over are similar or different, right? So our point is, if you can't say how similar or different two studies are, you also can't say how different you should expect their results to be, right? You just don't know, right? And so meta-analysis can't solve that problem, because the problem is not with the meta-analysis, it's with the raw material that the meta-analysis is trying to use. And so you can sort of think of this approach, if you want to think of it in terms of meta-analyses, you can think of it as a planned meta-analysis, where before you do the experiments, you design them in such a way that it's easy to do the meta-analysis after the fact, right? So that's with the one addition that you also are forcing yourself to make predictions, which in general is not what meta-analyses try to do. In terms of model versus theory, not to sound too flippant, but I feel like I know what a model is. I'm not sure that I know what a theory is. And you might think, come on, like, how do you not know that? But our experience of talking to people about this is that most people do think they know what a theory is, and they all think different things, right? And so I'm not actually sure that we have a great definition of theory in the social sciences. I was originally studied physics a long time ago, and I've forgotten most of it, but I'm sort of been wondering about this recently, and I'm curious what other people think. But my impression of physics is that theories basically are models, right? Like they're, that you write down a theory as an equation that you plug numbers into, and it makes predictions about other numbers, right? And so there's a very close association in the physical sciences between theory and model, which is sort of much looser in the social and behavioral sciences. And so I'm never really quite sure what it is that we mean when we talk about theory. But at least with a model, I feel like I can sort of write it down, and I know what it is and what it's doing, right? So that's the I feel sort of comfortable talking about models, and then we can sort of interpret them in terms of ideas that, theoretical ideas that people have proposed. But what does that mean in terms of a theory? I'm not so sure.
So for those of you who haven't read it, Duncan has, remind me the name of the article. This was like 2017 or something, where you're talking about, we have too many theories.
Yeah, so the first article that is referenced at the end is called "Should Social Science Be More Solution-Oriented?" And so it's motivated by this incoherency problem. And in that article, I propose that the solution is to focus on solving real-world problems. One of the difficulties that arose, after writing that paper, is that it's actually really difficult to think of real-world problems that are sort of not trivial, but also tractable. So many of the problems that we work on, or that we ultimately care about, are so big and amorphous that it's sort of very hard to know how you even define the problem or define progress. And so kind of the two articles, I think, which were published 7 years apart, display, I think, the sort of the development of this idea from let's solve problems to let's force our theories / models to make predictions. And that's something that's a much more generic and easily implemented solution, where some of those predictions are going to be relevant to real world applications. And so the kind of solution oriented part is still in there, but it's now a subset of this larger space of like, let's just force our theories, for want of a better word, to make predictions. And then we sort of at least know what it is that we know.
So it is now 3:00, and we have literally we have 20 questions that we have not yet gotten to appropriately. So we're going to send the 20 questions for Duncan. It's playing 20 questions with Duncan, and we're going to send those to you. And we also hopefully have by now put in the resources, also the links to the solution oriented. Should the two articles, Beyond Playing 20 Questions and Should Social Science Be More Solution Oriented, as well as the Newell lecture. So Duncan, thank you so much. You've given us to think about, and I think you've also given us potential steps toward a solution, which we're very grateful for. Thank you for being with us.
Thank you, Anna. That was fun, and thank you all for listening. And sorry that I can't see you all in person, but glad to get a chance to talk to you.
Great. Thanks, everybody. Take care.
Bye.